Who doesn't love making an ice cream sundae? Scooping ice cream into a giant bowl, pouring on that rich, gooey hot fudge syrup, sprinkling on some chopped nuts, smothering it all with a heaping pile of whipped cream and dropping a cherry on top. That is a great and tasty example of today's topic, additive manufacturing. You keep adding the next material into and onto the previous until you have manufactured your new electronics product, or tonight's dessert. Welcome to today's Tech Chat, where we chat with engineering experts about the latest innovations in the technologies that are shaping and reshaping our world. On this edition, we'll be discussing new advances in additive manufacturing with Sean Patterson, Global Chief Revenue Officer and President of the Americas at Nano. Sean has the technical background we always look for in our guests. He has multiple engineering degrees from the U.S. Naval Academy and MIT. And I don't want to give away Sean's whole presentation, but let's try to put out a little teaser for our audience. Nano Dimension is merely attempting to revolutionize the printed circuit board manufacturing industry and also develop entirely new products, including some cool 3D structures that I think everyone's going to find interesting. So stick around, and with that background, welcome to Tech Chat, Sean.
Thanks. Happy to be here. Nano Dimension is, as you said, trying to revolutionize the way we think about the manufacturing of electronics. And as we revolutionize the manufacturing of it, it revolutionizes the design. And I think that's the fun part. That's the game changer for the world. When you're able to manufacture differently and really remove DFM limitations that have existed in PCBs, since the PCB existed. And really try to help advance the design, to move it to a more sustainable process, to give more IP protection to our OEMs, and really just give designers art, the ability to make art in engineering, specifically electronic, but really electromechanical engineering by making 3D structures that aren't confined by 2D layers that everybody's used to.
Yeah, it sounds very exciting. I mean, engineers love to be creative, and so giving them new tools to play with is going to be something fun to talk about.
I think so. One of the things I did a TED Talk a while ago, and it was founded on the idea that engineer design is constrained by the technology tools that we've developed in the last X decades. And the example in sort of a non-engineering sense is Microsoft Word, right? The fonts you use are the fonts that are available, and whereas back in typesetting or when you were using pen and paper, you could be creative with those first letters in massive manuscripts and things like that. Now you're confined by the tools at which Microsoft gives you, because that's the most common denominator for their customer set. Now certainly you can go break out of that mold and do your own things at a bit map level, but what's available to most people in a day-to-day use is that, and you see that even in the engineering tools and the CAD systems that we have now. And the more that people grow up through their childhood, through then to through formal education as well, they're starting less and less to you're only learning in this digital gift, but that digital gift is defined by the designers of it, and it starts to constrain the education that we're giving our students to what's available. And it certainly works, but it doesn't. You're confined to the advancements of the company which gives you those tools, if that makes sense.
Yeah, very interesting.
We took a quote from Buckminster Fuller that you can never change things by fighting the existing reality, and to change something, build something new, model that the existing model is obsolete. And really, this quote is I think very relevant right now. I've seen a lot of posts on the business social medias like LinkedIn talking about all the reshoring that's happening. They got hundreds of billions of dollars almost now with the semiconductors going to reshoring effectively, Ohio, Texas, etc. And that's great. And PCBs and PCBA generally are left out of that. And the industry's, we need to bring PCBs back too. I totally agree. We need to do that. But if we do that and we do it the same way and we manufacture the same way in which we offshored it, we are, I think, running a fool's errand, because the memories of COVID and the supply chain constraints that have happened are going to be short. It's 5 or 10 years. If there's government subsidies that help this, that's going to go away at some point, and then we're going to wind up offshoring again because everyone will hate the cost. And so I think, at least in North America and Europe and places that are trying to reshore efforts, um, you have to do it differently. And that's what the technology centers of the world do well. You invent a new way to do something smarter. If we just simply do the same way that we manufacture circuit boards when we started to offshore it in the mainly in the 90s into the early 2000s, then it's a fool's errand. And I think we need to think about different ways to do that. And our company, Nano Dimension, has a machine that is printing proof of concept and prototyping boards in a way that we believe makes sense to bring in and reshore, but at the same time has all these by the ways of yes, and you can get it in X number of hours, and you can do 3D structures you never had. But it's going to take an effort, not just by our company, but really the industry to think differently. And we need more competitors in this space to push this technology, meaning then technology being specifically AME or additively manufactured electronics, because we have such an entrenched industry over the course of time. Whether it's standards that have been built around that since IPC was founded. And other standards that aren't IPC driven, and whether it's mil spec and automotive specs, things like that. We have to have other people come along with this and understand how to do things differently and support being creative to get through these early adoption phases. And I submit that we need to really do that to be different, or we're just going to do the same thing the way we always have in manufacturing when we try to do this. And so it starts with design and it ends with manufacturing.
Yeah, makes a lot of sense. It reminds me of the famous business book, The Innovator's Dilemma, where the people that keep doing the same thing
Mm-hmm.
and try to do it a little bit better, they end up fighting on cost. And then eventually somebody comes in looking at the problem a completely different way, and they end up taking over.
That's right. I was one of the bigger leaders in TTM technologies in sort of 2011 through 2016, 2017 area, and used to really say, how do we lean out this process, right?
Mm-hmm.
Everybody talks about lean or whatever the du jour consultant we're paying these days wants to call it, but it's still thinking about how to do things smarter, right? And I would just sit in front of a process and say, how do I do better? How do I do better? And we thought about things where we eventually got equipment manufacturers to lean in. Now, TTM being the 100-pound gorilla at the time, would able to get these mom and pop equipment makers to sort of try something new where we were collapsing flash routing with X-ray inspection and serialization with RFIDs all in one machine that went directly to a drill for optimization. And that's great. And that's leaning out these processes. But really the approach we're now taking in Nano Dimension is I would say it's almost the penultimate lean solution. It's take it from, out of design, click print from a CAD system, and outputs and certainly with our latest acquisition where we're going, a fully assembled PCB or electromechanical structure, not to confine our thinking to traditional PCBs, in one machine, in one print. And it's extremely exciting. I mean, we've printed drones, fully functional drones out of thin air. The motors are printed stators that are continuous coils instead of the traditional circle with a via through another circle to another via and right, and you get these inefficiencies in passive components. We're doing cool things like that, and I think ensure that arms are dielectrics, and we're working on different material sets for that. But the fact is, that's what you can do, and there's no assembly required, right? Or can you print a hearing aid? All of it, no assembly. The outside is a dielectric. Why not?
With that background, since many in our audience are probably unfamiliar with Nano Dimension, can you give us kind of an overview of the company?
Mm-hmm. Yeah. So Nano Dimension, as you can see on the slide here, we're reinventing electronics and production as a part of Industry 4.0. And it comes down to some of the things I defined. If usually ask these questions up front to customers of, have you been in a PCB manufacturing plant before? Now, less and less people have done that, but if you have, it takes a lot of footprint, a lot of capital equipment, a lot of chemicals. And a process that takes a very long time. And the more via structures you have, the longer it takes. And so when people started saying, yes, we've seen those things and it's problematic, there's just not a better way to do it yet. And the good news is, great, that's actually our vision, is we want to transform electronics fabrication and create a new paradigm in device innovation and then deploy them. And the way we start deploying it is not just, we come up with just the way 3D printers have done. We know that it's much more complex to do an electromechanical structure where the actual thing is a functional, like say, blob of material in the world. Meaning it's no different than in sort of like say 1930, nobody knew what a PCB was, and you fast forward to 1960, and maybe people are starting to understand. They created an electronic structure called a PCB. And now we're taking electronics and mechanics and putting it together. So an electromechanical structure that is sort of novel to the world, though we can print a traditional, multi-layer circuit board. But it's about the next part. So in order to do that effectively with multiple materials going down, a dielectric and conductive in the most simple case, humans are not going to be able to optimize that fully. And so we are building, this third bullet point here about intelligent, autonomous, and integrated devices, because it needs to really teach itself and take advantage of the AI and ML systems and deep learning that is now available in the world, so that we don't have to program it and it can self-learn. And then again, it gets into the delivery of environmentally responsible and economically efficient solutions, and then obviously enable the agile production of the 3D, and then empower production demand anytime, anywhere. We do view our future vision as sort of this distributed manufacturing. You tie it back to Gutenberg and printing presses and things like that, right? Well, now, you used to have to, you would write something down and somebody copy it and do typesetting and all that, right? A long time ago. And now desktop publishing, really, you have PDF or Word or whatever, Google Docs, etc. And you click print and it's printing next to you on your desktop. That's distributed printing, right? Because there is, people maybe even forget, there was this middle term there where you still had PDF kind of stuff, but you would send it out to a Kinko's or out to a printing facility. I think that's sort of the place we're kind of at now, where it's sort of contract manufacturing for that, and we want to make that. We want to eventually get to that desktop version now, albeit we want it in an industrial sense. So I don't think it will fit on your desktop right now, but that's sort of what we want, right? And so now you can have a printer in between the cubicles of engineers on the 8th floor of whatever company you want, and they have a printer at various spots. And so when you need a PCB or PCBA, really, you just click print, and if this one's loaded, it goes to the next one, and so you're able to sort of control that from an IP protection in your own house, or you can use hopefully contract manufacturers that are sort of more printing services, like there are many 3D printing companies out there now today that provide us a service, and that's what we really mean by sort of that on demand, anytime, anywhere. And you think these solutions are also providing things like when we go to Mars, or in situ things for the military, where you're sort of 3D printing the things you need, and you don't have to have the supply chains that are going across the ocean. So how do you solve those things? And we think this is a solution for that on the electronic side, of which there really isn't another solution right now. The industry has gone towards calling printed electronics, but it really is just metallization on the outside of things. Most of what people would say are competitors are just putting metal on the outside of things, which is a great use case, but it's not multi-layer PCBs, right? And so we're the only multi-material, therefore multi-layer solution out there. And we'd love it if there's more.
So those are some super ambitious goals. How long has Nano Dimension been around and working toward them?
So Nano Dimension started in 2012 in Israel, and so they've been at it. We've been at it since then. The Dragonfly, which is our core one, right? Core product right now. The Dragonfly 4 is the newest release. It released back then. They were originally tried as this desktop version, quickly found that PCBs are more an industrial thing. And so the Dragonfly series came out. I would say in 2016, things really started to ramp up. When I was TTM, I bought one of the first ones in the United States as an early adopter there, just fundamentally believing that this has to be the future, because there's just got to be a better way to do this. And so, they've been at it since then, since 2012. some great fortune that happened in sort of raising money last 2020 into 2021, January 2021, where the company was able to, as a public company, raise $1.5 billion in cash in the public market. And it's a very unique case for the company, where any company really, that was effectively had $3 million in cash and a $3 million valuation, and practically overnight went to $1.5 billion. And
Wow.
while that's a lot of money, you're like, ah, that's crazy. That is the kind of staying power you need to change this industry, though. It was not possible to do with a 10,
Right.
20, $100 million raise. There's just too many hurdles, right? How long was it going to take just to get standards agreed upon and changed so that, PE signing off on these things feel comfortable in the amount of, iterations, and not just assuming simulations will work out. You got to get these things in the field, meaning the PCBs that are coming out of the back of it, right? The 3D
Yeah.
structures in there and field tested. And so it does take that kind of staying power. And the I would actually submit that we probably have the largest R&D budget, if you're considering the 1.5 billion, which is really mostly R&D, in the world. Like I don't think, the big companies that would think this is a big enough problem to throw that kind of cash at it. And we were just in a fortunate position to do that. So really, since April 2021, the company's practically new from the amount of people we've onboarded. I mean, when I started in the United States in June, we had 5 people. We're about 38 now. Globally, we were about 60 before we raised the cash. We're over 500 people now. And so we're putting the right engineers in place, and the right business leaders, to really ensure that we develop the ecosystem that supports a new technology like this, and working directly with the OEMs and getting them comfortable, and then bringing up manufacturers to be able to still do contract manufacturing. So it takes that kind of cash, I believe. And hopefully this is enough to pull it off, if we have enough support from the industry, knowing that they want to do something different.
So you just kind of hinted, most people look at the PCB industry and don't see that as a big enough problem worth investing the kind of money you're talking about, because they don't think it's broken. But tell us what you see when you look at the industry.
Well, having been a general manager of a PCB plant, and a PCBA plant, and then multiple plants, um, it's a manually intensive process. Unless you have high throughput of the same board, by the way, not the market we're going after, in overseas, really, you really can't set up machine to machine handoffs. And even as the materials get thinner and thinner, even at that, they have handling issues in the East with these automated loaders and unloaders and things like that, especially when it's in the core phase. And so it's very hard to automate it. And so we're going to just dump a bunch of money into figuring out better robotic handlers, and just take these small quality defects that happen, and fix it. I'm not sure. I don't think that's the right answer. The one thing with a PCB and the manufacturing of PCB, which is no different than a semiconductor in some ways, that I don't think people appreciate if they haven't gone to facilities, is that you work on these things for sometimes months, the same exact thing, like massaging the same ball of clay over and over and over again, putting 100,000, I'll go with 4 mil vias in there, right, before lasering, and you can't bake that drill bit at all 100,000 times, and then you got to get fluid through it where it connects in all of them. And by the way, one of the holes doesn't work, scrap board, start over again. I don't think there's an appreciation. I think definitely some purchasing managers and buyers would know it for how many times the board shop will call up and say, "Hey, we scrapped it." And certainly as the industry in the PCBs at least tries to chase semiconductors getting smaller and smaller, and they have a much tighter control of their supply chain because they make products. They're not contract manufacturers, really, right? There's only so many processor designs out there at any one time in the world. There are way many iterations of PCBs, right? Every single one is different, and so I think that the OEMs in particular have lost touch with it because OEMs used to manufacture the PCBs in-house. Mostly all of them did. And then it got too complex, or they couldn't get the utilization up, and they start shoving it off to contract manufacturing. At least on the bare board side, some have kept the PCBA. But then others, moved it off to TMS, and that have really slim margins. And so it's hard to invest in new stuff where there's not a demand coming from their customers, and their customers are multiple, it's not just one. And so I think that the industry kind of just doesn't know, except that they just don't get their boards on time, and it gets even worse as the yields. Again, the semiconductors pushing things smaller and smaller, and the PCBs can't keep up with it. It's a real big problem at Mil Aero, where they don't want to redesign, or they don't have the talent set to redesign, and they want to still keep 3-ounce copper traces, and then say, well, yeah, but I want to put a really, really tight BGA pattern in the middle of this. And they don't understand that these flux patterns don't work out very well inside of plants, and they drive up cost. And they may not feel the yield issue, but they might feel it on a cost side, which they don't even know about, because the PCB shops know our yields are so low. And I think there's just tiebacks to it, maybe just a lack of understanding, as these things have moved off, and engineers don't go out to the supply chain anymore. Maybe it's even worse now with COVID, where you don't even get to see those things and understand the problems. So that's one. In terms of environmental, like, we're night and day. Think about how much copper is removed from a board that has signal layers at the end of the day, right? You start with a complete sheet of copper, you put this image down. Even if it's a very dense image, when you get sort of 2 and 3 mil traces, you're still talking north of 90% of all the copper's gone. But we mined it all, we produced it all, we threw it through everything. The industry even has a thing called an etch off, which means take all the copper off. We just need the laminate, right? It's crazy. And you can think about how much, when we look at our environmental studies, we just stay onto the PCB plant itself. But when you really think about it, like, how much you would change if like 50% of all the boards went to a 3D printing, we're only putting it on the metal you need, how much less mining you would have to do. And then how much, that saves. And we're not even trying to get into those crazy things, right? And so I think there's that from an environmental sustainability point of view. The amount of water using is crazy in PCBs. The amount of chemicals is ungodly. Like an EC line, or electrolysis copper line, how many different chemicals are in that thing? And by the way, if you add the wrong chemical to the wrong bath, you get chlorine outgassing, and all these things. You ask anyone that's gone to a plating shop, the PCB or otherwise, and they'll tell you there's a certain smell in the air. They just can't pinpoint what it is, right? And so there's just environmental issues that are associated with it. There's certainly IP issues for intellectual property protection. And it's tough to keep those designs, in house, right? And you also need to protect at the I'll say the pick and place level to have the full component list, and you can reverse engineers things pretty easily if you're not careful with where you're sending your information to. And so we offer that, right? Because you can print in house, and you don't need more than a football field size factory to do this. So you can really have that printer in house, particularly during developmental phases at an OEM, even if you go contract manufacturing after that. And then it is slow. If you try to get quick turns, you start talking $5,000 just to get it, in a week, if the number of via structures is not crazy. I used to have boards that would take 6 months to make, and if you scrap it on the 5th month, start all over again. And so it is a slow production process, very iterative. Again, that same ball of clay. When you 3D print these structures, the complexity is free.
Right.
How many via structures doesn't matter. And maybe we stop calling it vias. We were talking about maybe just like rebranding it to structure, not a via, or like any layers. Maybe it's any structures. I don't know. We need to think about how we kind of position it, because it's true. Like, you don't have to have microstack via, stacked micro vias, things like that. Which, by the way, the industry is even concerned about reliability on. You can add in 3D. You can do whatever you want. You can have a circle. It doesn't matter. In the z-axis, right? And so that allows you to reduce the lead times. So when you're competing on just like a premium quick turn from a prototype, this wins, and it certainly wins from the amount of engineering hours where the OEM is, the engineers, for lack of to be crass, are sort of sitting around and twiddling their thumbs waiting for the board, and then they get it and they realize, oops, we made an error, and then they got to do it again, right? And waiting 4 to 6 weeks on it. That's the time that our current machine really, really saves. And then certainly when we talk about proof of concept, that gets into things that you can only do in a 3D nature. But only doing in a 3D nature requires design creativity and the design tools that we've developed to actually get there as well. So I think those are the 4 main areas. Again, sort of 3D design, the IP protection, the environmental, and the supply chain sort of slow production.
And so please tell me, since you're aiming for the stars in the PCB world, that you're going to move away from mills.
Yes.
The only industry, I think, in the world that still lives on mills.
Yes, our footprint, we talk in millimeters. Now, to be fair, the machine's made in Israel, so we're kind of forced into it. So technically, our current machine is 6.29 inches by 6.2, and some repeating
Right,
decimal
right.
point.
So, since supply chain has been a rather newsworthy topic the last 18 months or so, tell us more about this particular issue and as it relates to your PCB manufacturing world.
Yeah, so I think, I've touched on it certainly during the conversation here, but maybe just to kind of tie it in a bow here. Supply chain issues. Is our machine going to solve today's supply chain issues? Like today, like engineers buy it, I'm going to print this circuit board and put it in a plane. No. Now, that's where we want to be, and we actually don't think it's that far out for us, especially with the fortunate capitalization we have now, where we don't have to spend forever doing R&D, and we can buy the solution and integrate it versus hope that we can solve it in an in-house R&D fashion, right? But in terms of like the future supply chain solving, you will have the printer in house, so there really isn't supply chain associated to the bare board side. And even for those unfamiliar with PCB production, really the actual raw materials in PCBs is not complex. Like, it's not a complex supply chain to PCBs, right? You have drill bits, you have the laminate and copper, and then you sort of have support materials that go on it as your manufacturing end, right? Whether it be photoresist and things like that. And I'll put solder mask in that same category. Um, so there's that, right? But when I was thinking about it, you don't you actually solve the supply chain issues all the way back to the mines, for instance, right? Because you need that much less metal. We don't have to manufacture those laminates and coppers outside of the country that's using the machine, because it's not a huge supply chain to create it. So you're actually solving it beyond just the PCB. But when there's these microchip shortages right now, even just to say, all right, we're going to expand PCB capacity. Well, every single one of the capital pieces of equipment that support that PCB line are wind up in the same exact
Yeah.
supply chain issue just to make the machine that makes the machine, which makes the circuit board, which goes the chips on. Is like this incestuous cycle, like feedback, negative feedback cycle, right? And so I think it actually really blows that out. Again, it's not solving today's problem like tomorrow, because you can't get your Tesla on time because they can't have it. Not, but our goal in a very short time frame is to have that machine that would solve it literally tomorrow. Um, so that's sort of what I think about from a supply chain issue. It's not just the PCB, and I can't get the PCB on time, or the semiconductor, right? It's about the supply chain of all the raw materials of that, and including the capital equipment sets, and that was tied to the expansion and all that. I mean, I even wonder what's going to happen with these big fabs that are going up now, right? The amount of technology that goes in there, it gets caught unto itself, and it's this sort of self-fulfilling prophecy. But again, we think where we're trying to go is a parity of machine that people will be comfortable with from a throughput side for high mix, low volume. And today, low volume is sort of ends at the automotive throughput, meaning electronics for cars. Anything sort of beyond that, we're not really going after, but we can do sophisticated things, particularly with that antenna design, for example, that might be applicable to cell phones, but we're not trying to go after that from a throughput perspective at this time.
Well, that makes sense. So, you've really introduced some of the problems to us, and now tell us about your solutions.
Yeah. So the solutions are how you design. So we have the solution. The solution we're saying is this 3D printer, right? Multi-material, multi-layer 3D printer. But the real solution is what the designers come up with. Because while we can just do a 2D or 2.5D, if you'd like to call it that, since there's vias circuit board, we can print that. And does it print? And it lights, all the LEDs light up, and it's functional. Yes. That's not the real juice. That is from like when you start attacking the bigger market, which we're going after again on the next machines. But it's really, how do you think about it differently? Everybody's like, oh, I need flex, flex, flex. Yeah, but if you actually redesign what you have, you actually don't need flex. Because flex is doing it because the form factors are getting so difficult, and you don't want to do, cabling harnesses and all this kind of stuff. But if you had any shape, I'll say any shape kind of circuit board,
Mm-hmm.
right? There's just like any layer,
Mm.
any shape. Do you actually even need the flex?
Interesting.
Maybe not. Do you actually need a server stack that is pick your X standard inch deep um, server stack because you had to get all your components on in a planar manner in a 2D manner on the top when we can actually embed components inside active components inside of our boards and build it up, and we do that today, and there's some good examples online. We call it like a 3D cube, still rectangular. I mean, you can make it circular, it doesn't matter, but our good one today is a cube that used to be a flat PCB that was 60% bigger from a XY point of view, right, on area. And so the solutions are really coming from the designers and the faith of the engineers that, from a reliability perspective, that support those designers. And I think that's the exciting part for me. While yes, we can do, and this is the Harville elevator pitch for us, is we have a 3D printing circuit board machine because people just think, okay, I've had the circuit board printed outside, you pick your place for 50 years, can you print it? Yes, but that's not the point. So again, that's where I look really to designers to come up with these creative solutions. And so we're expanding our engineering capacity from an application engineering perspective to really do inception of ideas into companies, whether it's a phased array radar that actually is pyramids now, has little pyramids that have radiators on each one of the four pyramid faces. So you can get phased array radars, which used to be wire wrapped and all that kind of stuff, and then it went to PCB, but the PCB had to flatten the entire process. Now we can bring topography back to it, and sort of have or one example that we did where we did continuous coils to the radiator on all four sides. And if you can sort of not just do phase separation, but you're also getting help now with a separation between the faces coming in, right? The sorry, as the signals coming in, you actually have it also from a geometric offset and not just the phase time separation. Those are kind of unique ideas. When I gave the example of the cube, or we're printing a drone right away, right? Printing motors and the motor stators of that drone. By the way, the full version of that drone runs at 2,300 RPM with printed motors. It works. So again, that's where I would look at solutions. We have the platform that designers can then use as a solution, if that makes sense. You'll see the phased array radar that we did there. That's actually the sort of artist rendering of it, but we did print it in reality. But our company's not going to go through and do the entire back end of this system, and how are you going to do digital processing and all that? That's not our wheelhouse. So that's where we need the designers and the OEMs to develop those solutions. But we can give them the idea inception, and then hopefully the snowball starts picking up more and more. I get more, and then these sort of ideas just keep on coming out. We also have an example of a coil board, right? Actually, very hard to manufacture traditional from a yield perspective, because there's a lot of shorts that happen between those coils. But we can also do continuous coils, right? You don't have to, again, have vias connecting everything. We have an example there with connectors on the edge, on the upper right. And again, very, very tough to traditionally manufacture, and the yields are not so good. So we can get edge connectors. We can put components on the edge, as well as inside of the board. But that's another good example. Obviously, there's another 3D printed antenna there, and a flexible circuit, albeit with a rigid dielectric material, but it's still, if you print it thin enough and do some other things, you can actually get it to bend, for sort of biomedical sensors and things like that. Some of the easier things for engineers to kind of get behind in sort of first use cases are redesigning, as I mentioned before, the sort of size XY area of the PCB, and you can get it into a 3D structure and therefore shrink your area. And that allows for miniaturization. We do see in the RS spectrum, even though our DF isn't as good as like a Rogers type material yet, the change in parasitic effects for passive components in RF systems is better, is as close to the textbook equation for doing doing calculations of inductors and capacitors than anything else. And so you can just set up these awesome, low pass filters, for instance, that take no components, and you're just making capacitor boards and without capacitive materials, and where you can fit. I'll use layers, but it's a 55 layer capacitor in the space that you would have two sheets of laminate in a traditional PCB. And through that we can get really good low pass filters. If you need shielding, we've done all these tricks over the course of time in PCBs to maintain impedance control, to do EMS shielding. Well, if you really need the shielding just on one line, just print the coaxial cable down the middle. You can print the cylinder, sure, and we've done that. And so you don't need to worry about stubs from back drilling, and reflections. You don't have to have these 90-degree turns, and so that's where we start to get more efficient. But you have to start with design, and then we also have to meet the industry with better performance materials that go through 3D printing deposition methods. Our current one being an inkhead, and there's tons of other sort of deposition methods for various materials. Um, and so we want to meet the industry halfway, but you have to start now. It's not like, oh, I'm going to wait until you guys have all these 10 different materials and the printer is printing at 100% yield. I think that if OEMs wait, they will be behind the eight ball, because it's not trivial to get engineers to think differently and to get their bosses to be comfortable with reliability. And so I think it will take 2 or 3 years, and why it's important to get in the water now with these machines that print the prototypes and the proof of concepts, so you're not fielding those circuit boards. But again, they're functional, but you're teaching your teams, and you're thinking about your roadmaps, and you're getting involved with a company that has a very, very large R&D budget to try to change what we're doing. And hopefully other companies come around trying to increase competition and drive the industry more forward. So I think now's really the time to be getting in the water.
Yeah, so you're kind of like creating the Photoshop for artists, and
Mm-hmm.
allowing the artists to figure out how they're going to use it, and you let their imagination run wild. But you're creating that canvas and that space for them to innovate.
That's right. So we had to take, we have a new software called Flight software, which is effectively, I like to describe it as, you design your circuit in ECAD and use all the great things that are available there, from netlists and all
Mm-hmm.
this kind of stuff, right? And then you import it through our APIs and plugins to 3D softwares. And then what I explained is you sort of put it into a 3D software and then explode view the pads up to the surface that you want, to the topography that you need.
Creating these things, the equipment is going to have to look different than standard PCB board manufacturing. You're not going to have reflow ovens and that kind of stuff. So tell us about that equipment.
Yeah. So again, with our fortunate capitalization, the approach here is sort of buy and integrate, and we're doing R&D as well. So the Dragonfly 4 is actually the one in the upper left there. One of the first acquisitions we did was DeepCube, which is a machine learning for deep learning on board, an industrial deep learning machine, not trying to predict consumer buying behaviors like a lot of the sort of scientists are going towards, because that's where the money's at. We're trying to be industrialists with machine learning, so that's what DeepCube does, and that helps apply the brain to our equipment to sort of self-correct as it's going along. We also acquired the Fabrica Group, which used to be Nano Fabrica. Now that's the Fabrica Group, and we have the Fabrica 2.0, which is a machine up there. That's a machine that does traditional DLP type 3D printing, but 1 micron resolution, all 3 axis. And it made sense to us because we think about sort of like pure lab on chip, where you have microfluidics and sort of little mini pumps on the electronic boards. And so there's things from an assembly point of view that make sense, but we also need optics that start to get down to micron resolution on a PCB. Today's machine with just ink heads prints at 75 microns. And so while we can get smaller with that, we do need to think about other technologies if we want to really blend the world of semiconductors into PCB, where you can do, and we have done, direct chiplet on board, and you just print the wire bonds. And so as those wire bond connections on the chip get smaller, then we need to be able to shrink it to that area and then explode view it. But we just don't have the issues of traditional fab, where you have these fluxes and plating tanks and things like that. So we acquired that group, but we do sell a machine there called the Fabrica 2.0 that does that. And then we acquired SMTech, which is a pick and place and dispensing company. They're one of the only machines that does pick and place dispensing and jetting in the same machine. So really good for MPI areas, right? So you put your solder paste down, you can do, and then you do your pick and place, and then you can do underfills and stuff like that all in the same machine. But we acquired that technology because our ultimate solution is to have fully embedded pick and place and soldering inside the machine. So you can have fully embedded active components. And we can do this today. We just stop the print, take it out, do it, and then put it back in. But that's why we acquired SM Tech, not only for its product lines, which we will continue to sell, but to be able to build that future machine by a company that already has integrated multiple functions into a single head. As part of our next systems. And then we acquired Global Inkjet Systems, which is us going vertical to be able to control and engineer the actual deposition methods of our inks. I can't really think of it too many equipment developers that have gone all the way down to the print heads or the deposition methods, because really those print heads are really being driven by the printing industry, the ink printing industry, and 3D printers are sort of making use of that, but it's not, that's not really demand is sort of going for the print heads in terms of changing the engineering and the controllers and everything. So really owning where I say where the science meets the engineering, right at the edge of where the ink's coming out at the ink head to then deposit on our substrate. So we acquired that as well, so we can really drive down to fine resolution with the type of materials we're trying to put through. So those are the acquisitions that we've done thus far in about
Yeah,
1
it's a
year's time
lot.
that way.
Do you have application labs where customers can come work with you to evaluate the equipment, get some hands-on help at how they might use these for their products?
Yeah, so we do in Israel. We do in Florida. We're actually moving all that up to Boston right now. I'm actually sitting in our new Boston office and expecting our first machines here on Friday. And we've doubled down on the engineering resources in the United States, application engineers. It's not just typical application engineering support. We really need to do, our pre-sales, how they think about a new design, but then it's all this post-sale support, because it's almost like once you come up with an application, it's fine for our customer. But when they need to go into the next application, they need help right now, because again, it's a different way to think about things. So we're building it out in Boston. We want to be close to the heart, at least in the Americas, of academia and some really good industry in the Boston area. Because again, it does start with the education to get people and students that are unencumbered by the past to think differently. And so we're working with universities, no different than say, when the original Apple computers came out, they were almost giving those things away to elementary schools to get, really young kids used to this. And that's why we're now in Boston. We do have these labs. And I would say, I don't want to put a total date on it as commitment, but I think in the next month and a half, people can come here and try their designs. But we can do that today. It's just a lot. It'll be a place where people can come and see versus sort of ordering it and maybe don't want to go to Israel or whatever to kind of see it be designed. We also have labs that are being set up in Germany, Munich as well. I was describing a 3D cube before, and so this is the actual 3D rendering of that cube. And it maybe to the fast look looks like a PCB with vias, but if you actually look deeper, there's actually pipes. It bends. It doesn't make a 90-degree turn at the bottom of some of the vias, particularly ones that are maybe the third sort of pad up from the center there. You can see it's actually it's more like pipes, like a piping design. And so these are all the different structures that one of our customers did to redesign a PLL into a 3D structure, and they really saved a lot of material, again, area. And so that was an actual design, and today we can do that. You just click print as an STL file from a 3D software, and it works. And this one actually has active embedded components in the middle.
Oh, fascinating.
In I think 3 different layers of active components. Again, the concept of layers kind of dissolves with this. It's more about structures, but sort of think of it as 3 layers of active components.
Yeah, it's fascinating. You don't have to think about straight lines. You don't have to think about layers. It's just where do you want it in this space?
Yeah, or even if you look at the via on the left-hand side corner, it's again
Mm-hmm.
the left of the image. There's actually like a trace that goes down at an angle.
Yep,
It's a fat trace coming
I
down
see that.
at angles, and so you can have like that's crazy, right? You don't have to have round vias, even if we can do 45-degree round vias, but let's not think about that. Let's think about something crazy. Like again, it's up to the designers. I mean, we have some people doing trio twisted wire pairs around boards for various purposes. Um, or again, coaxial cables, and it's limited by the creativity that the engineers that don't yet know how to think yet, right? But I haven't met an engineer that doesn't get it. Once the picture's worth a
Right.
thousand words, if you will, right? It's just a matter of are they ready to accept moving that way and being early adopters within their company, so that their company is prepared for the sort of again revolution of the industry we're trying to push forward here.
You spoke earlier about your Deep Cube learning software. How integral is that deep learning and AI to your additive manufacturing flows?
It is integral. We the first sort of stuff we do is not nozzle cancelization with it, which instead of using humans to adjust things when things are going wrong, but we want it. We're using it to fundamentally feed layer by layer the adjustments to in perfect processes. No different than every other manufacturing process in the world, right? Except we get to do it each pass of the printer, and you can adjust it on the next pass and the next pass as you build it up. And you just don't have that ability to do in traditional manufacturing. You could do it after some steps where you some like plating step, but then you have to get to certain areas where you can actually do electrical tests and things like that. We're almost doing like a permanent AOI all the time. And so we're looking at improving the yields, consistent yields, faster R&D. Again, I talked about before about the engineers kind of sitting around. There's definitely a value add there on today's machine from a prototyping point of view. Sustainability, we've talked about several times. And then our agile response being how fast we can do the R&D, and then IP security, which is a really big deal, particularly as we get comfortable with not offshoring things. And then all of that supports brand new designs that people haven't even thought about today. The drones from thin air, the hearing aids, different sensor systems for biomedical, and that's the really fun stuff that I really hope to see these creative engineers come up with.
Well, thank you, Sean, for that introduction to Nano Dimension and apparently your goals to take over the world.
We want to help revolutionize the world
Yeah.
for a better tomorrow. I mean, honestly, it's a very altruistic thing that we're trying to like. When I talk about AME, like we want to push AME for the world. That it is a sustainable process. That we get all these creative designs. And do we make the only ones that do the machine right now? Yes. But I've said it several times today in a very honest sense. I would love if there's more competitors in the space that help drive new materials and things forward and different platforms, because it would be hubris to think
Right.
that we would do all of it. Um, and and so I think it's the right thing, 3D AME, what I'm talking about, not from a printed electronics, which is sort of what the IPC has thought about
Hmm.
traditionally. Can we really get there on a multi-layer, meaning structure, getting creative design? Can we really get there uh, differently? And I think we can. And we're here to help support that, and we're looking for companies that want to be these early adopters who believe that this is the future. And that's again, that's why I bought one of the first machines in the US. Is I can't see a future where it's not the thing. Now, is it 5, 10, 50, 100 years where it's everything? I can't bound that. And I think the original mechanical 3D printing got tried to time bound it too much, and now there's turbofans, blades being printed metal, and people are flying in those things now. And so we want to get there with electronics, and it's just a more, maybe it's a risk averse community, and certainly the people that have done the fan blades, I wouldn't say that's not risk adverse, but the entire industry of electronics is risk
Right.
adverse. And so that's why we're starting with the universities up here. So if you're in the Boston area, please contact us. You can definitely get a design, or you can get a co-op or internship with us. But again, we're really taking it from, can we be sustainable, can we get the industry to be different, and we just want to be a part of that revolution, and certainly help lead it. And there's plenty of money for everybody to be that, and plenty of new ideas really that come forward from the engineers. So that's what we're here to help do.
Well, Nano Dimension is definitely a company that we will all be keeping an eye on in the coming years and see how you progress toward these goals and see how the industry and the other companies bounce up around. But if you'd like to learn more, I'd encourage everyone to go check out their website at www.nano-di.com. And that wraps up this edition of Tech Chat. Please join us again as we chat with the leading technical experts in the electrical engineering world, like Sean Patterson, and companies like Nano Dimension that are changing the world through electrical engineering. Thanks.